Hello, how are you? How are you doing? It's the pioneers, the Tunisian researcher, Mourad Sultan Ezouidi. Just today, I will introduce my theorem that had been generalized for any degree from an equation, and it's the occasion for you, my colleagues, to uh, known about this fact. Okay, so prepare yourself, and we are here to explain what's needed exactly. Okay, okay, okay. I'll give you time first to prepare your papers. And okay, I'll share this first. Facebook and Instagram, so that professors, colleagues, whatsoever can benefit from this lecture. Okay. So here, hello again. How are you? How are you doing? It's me, Mourad Sultan. Really, today we will see how the theorem works. Okay, how it comes you theorem PDF. Okay, I will make it bigger so that you can see it. Okay, like that. This is the apex. I will reduce a little bit. Okay, so that you can see the whole structure of my standard form of n degree from equation. Here is a 14 degree from equation. Just I will suppose that is everything from equation, and then I'm going to write my theorem. Okay, so you can see that this is the theorem of Mourad Ezouidi. Okay, this is the theorem. We will explain the theorem. How does it work? Okay, for finding the exact roots of any given equation, and to explain this recursive formula, how does it vanish all the coefficient of the new n degree from equation corresponds to the original n degree from equation. So we will start. Okay, hello. I will put this here. Okay. So here we start.
Degree 14. Standard algebra often, just doesn't cut it.
You usually end up falling back on numerical methods, approximations.
And that's the big limitation the sources are highlighting. These numerical methods, things like Newton's method, they get you close, sometimes incredibly close.
But it's not the answer.
No, because you're dealing with floating point numbers, rounding errors
This is the
creep in,
theorem.
approximation, never the
Okay.
true precise value.
And then there's the deeper theory, right? Like Abel's theorem.
Yeah, the classical stuff. It tells us that for general polynomials, degree 5 or higher, there's no universal formula using just radicals, square roots, cube roots, that kind of thing.
So some equations are just fundamentally unsolvable by radicals in that classical framework.
Which leaves us wondering, are we just stuck with close enough for these complex ones? Or accepting that some just don't have exact solutions we can write down easily?
Well, that's where these sources get really interesting. They introduce this idea,
Here
Mourad
goes
Sultan Ezouidi's theorem,
theorem.
and the claim is quite bold.
It is. It claims to offer a way to find exact symbolic roots, even for polynomials that seem impossible with traditional methods.
So the sources suggest this method is, well, different from the classical toolbox.
Yes, completely distinct. And it even suggests that some polynomials we thought weren't solvable by radicals can actually be solved exactly using this alternative framework. It proposes a systematic process.
Okay, so that's our mission for this deep dive then. Let's unpack Ezouidi's theorem as presented in your sources. We need to figure out how it supposedly solves these things, like that 14th degree example, and aims for exactness where other methods approximate.
Sounds good. Let's start with the specific polynomial itself.
All right, so the sources lay it
This
out.
is how
Ex
the theorem works
equals.
for any
Okay, here we go.
degree
X star euro minus x zero plus
This is
zero,
my
and it
theorem.
continues alternating signs
Theorem
down to minus narrow x plus 0. Just seeing degree 14 written out like that.
It's daunting. And the sources give specific values for these ill-Q coefficients relative to something called 2Q. Let's see. Nauro is 14. Nauro is 91, is 364. Goes on. Nauro is 432. Then Nauro flips to negative. And answers 1T997. All the way to Nauro equals 1. It's a very particular set of numbers.
A very specific setup. And the source actually gives a hint up front, doesn't it?
It does. It mentions that for this particular polynomial, that1 is actually a root. Not just once, but with multiplicity too.
Okay, so that's a known piece of information provided in the material, a starting point.
Mm-hmm. So now think about those limitations. We talked about the approximation errors, the classical solvability walls. According to the sources, Ezouidi's theorem is meant to sort of sidestep all that.
How? By offering a fundamentally different route to the roots.
That seems to be the idea. Instead of iterating closer and closer or hitting that no radical formula barrier, it claims to provide a direct path to the exact symbolic form of the roots.
So, how does it actually do that? The sources mention a key formula, a process.
They do. The engine of this thing, based on the sources, seems to be this formula for calculating some intermediate values. They're called Farja.
Okay.
And the formula looks like this: times equals the sum. From dir to k-us.
This is a form
Oh
of
dear,
pi.
times raised to the
1
power
to 3
times a
k and
flugo.
how does
Whoa, okay,
it
that looks
to apply this
complex.
formula to
Let's try
find
to break
value
down the idea behind it
or
based on what the sources say. It
exactly
seems to involve
way
calculating a sequence
corresponds
of
to
these
the
coefficients.
previous
That's the
formula
gist.
we started
You
with.
calculate
Okay,
them one after
but in
another.
certain
Think
instance
of them as symbolic building blocks. The calculation for each one, like now, uses the original polynomial's coefficients, those felt terms, and also relies on the coefficients you've already calculated. It's recursive.
Right, recursive. And I see these other bits in the formula, Unduna and Guy. The sources say the C part involves binomial coefficients.
Yeah, those pop up a lot in polynomial stuff. They're related to combinations, adjusting terms, and the sources mention way relates to the polynomial's degree in the calculation somehow.
Okay. And that term brings in the leading coefficient too. So it's systematically combining the original polynomial's DNA step by step.
Seems like it. It's using those original coefficients recursively to generate this new set of t's coefficients.
So the key thing here isn't plugging in numbers and getting decimals, right? It's doing all this calculation symbolically.
Exactly. That seems to be the crucial claim in the sources. Because you start with exact coefficients, and each step is just symbolic manipulation based on previous exact results.
You never introduce those pesky rounding errors. You're always working with the true representation of the number.
Precisely. You maintain exactness throughout the process.
The sources also showed some patterns like binomial coefficients.
Yeah.
1, 14, 91, and 1, 1378 popping up. Is that related?
It seems likely. The sources suggest those patterns are kind of inherent in how the formula uses combinations to build up these symbolic coefficients from the original polynomial structure.
Okay, so you calculate these e's coefficients all symbolically, all exactly. Then what? How do they lead to the roots?
Well, the sources state that these EBS coefficients directly relate to the roots once you have them calculated exactly.
You can derive the actual roots from them, also in an exact symbolic form.
That's the claim. The E's coefficients hold the key to expressing the roots precisely.
And this is where it gets really interesting, potentially groundbreaking if true. The outcome described is finding these precise roots, even for polynomials that we'd normally just approximate.
Or even ones that classical theory might say aren't solvable by radicals. This method, according to the sources, claims to provide exact symbolic roots regardless.
It's like a completely different way of thinking about solvability.
It seems to be presenting a framework where algebraic exactness isn't limited by the classical constraints or the practical issues of numerical methods.
Okay, so let's sum up what we've unpacked from your sources in this deep dive. We started with the challenge. High degree polynomials are hard to solve exactly. We rely on approximations, and classical algebra has limits.
Right. Then we looked at Ezouidi's theorem, as presented here, which proposes this alternative route
A systematic process using a specific recursive formula,
to calculate these symbolic as coefficients exactly.
which then allow you to find the exact symbolic roots, avoiding approximation errors, and maybe even bypassing classical unsolvability definitions.
Yeah, it really underscores how exploring totally new mathematical angles might crack open problems we thought are settled, or at least problems where we accepted limitations.
And it's not just about this one, admittedly very complex 14th degree polynomial, is it? Solving that exactly would be remarkable, of course.
But the implication is much wider.
Exactly. It leaves you, the listener, with a bigger question to chew on. If this theorem, this different framework, can provide exact symbolic solutions where we previously relied on estimations or thought radicals weren't enough,
Then what other really complex mathematical puzzles out there, things we currently tackle with approximations, because exact methods seem impossible within our current toolkits, might actually have precise exact solutions if we could just find the right, perhaps completely new theoretical lens to view them through.
a really fascinating thought sparked entirely by the sources you brought us. Thanks for sharing them for this deep dive.
Okay, so we continue. We thought that this is our theorem that had been generalized, and after 14 years of work, we reached this fact that sk minus 1 of the q is equal to the sum from 0 to k combination n minus r choose k minus r and raised to the power r between parentheses negative by 0 for the q raised to the power k minus r times lr minus 1 for the q. This is the formula. This is the recursive formula. It's called also discriminant formula or theorem of Mourad Ezouidi that will help you to find the new nth degree polynomial equation corresponds to the previous one. Okay, so thank you for listening. See you inshallah next time. Okay, soon inshallah I will be live with you to explain 14 degree polynomial equation and how this 14 degree polynomial equation has been written as a subset of x raised to the power 7 all squared. Means the 14 degree is written as a 7 degree raised to the power 2, or in other words, 14 degree can be written as the square of a 7th degree polynomial equation, meaning that we should solve the 7th degree polynomial equation that has been raised to the power 2. Then we go back to the recursive formula and conclude the 14th exact roots of the 14th degree polynomial equation. Now I will start doing this example. So prepare yourself. And here is, and then here in my live stream, you will be benefited, of course, 100%. Okay, and we will apply new theorem of Mourad Sultan Ezouidi. Okay, thank you, and wait for me for a while moments. Then I'm going to start to be live with you. Prepare yourself. Prepare your scientific calculator, your paper sheets, and your pens, and try to get the point how to master the solution of nth degree polynomial equation. We told nth, not fourth, not fifth, not sixth, not seventh, nth degree polynomial equation. Okay, so here we just tell you goodbye and see you soon, inshallah. Okay.